So Claudia and Rob, the stage is yours.
Okay, perfect. So it's a pleasure to introduce Rob Scheichl today. Since 2018, he's professor of numerical analysis at the University of Heidelberg. And Rob got his PhD in mathematics from the University of Bath, UK in 2000. And then he was Marie Curie postdoc fellow at the Institut Français du Pétrole in Paris. In 2002, 2 years later, he came back to Bath, to the UK, and became senior lecturer in 2010, and professor of scientific computing in 2011. Rob has more than 20 years now of experience in numerical analysis, scientific computing, and uncertainty quantification, with a recent focus on advanced multi-level Monte Carlo methods, Bayesian inference, and learning also from sparse data in high or infinite dimensions. He's one of the pioneers of Quasi-Monte Carlo and multi-level Quasi-Monte Carlo methods for efficient uncertainty quantification in highly complex problems. And today he will talk about multi-level Quasi-Monte Carlo methods for PDE eigenvalue problems. So we are very much looking forward to your talk.
Thank you very much, Claudia, for this nice introduction, and Andreas for a nice organization, and the others in the local organizer team for nice organization of this meeting in these difficult times. I enjoyed it so far, and I hope that I can present to you some interesting results, which are joint work with Alec Gilbert, who used to be my postdoc here in Heidelberg for a couple of years, and who has gone back to Australia, working in UNSW in Sydney again. So this is a continuation, as Claudia said, of work that we've started a while ago on multi-level Monte Carlo and Quasi-Monte Carlo methods, and then marrying them. And in this particular talk, I want to show you how this can be extended to PDE eigenproblems and why this is of interest. So I will motivate, give you some examples of eigenproblems where the problem occurs that I'm talking about, and then show you how this leads to a high-dimensional quadrature problem, and thus to sort of a typical application of Monte Carlo type methods. And as we've heard already in many talks here, and people know anyway, when we are talking about complex engineering systems that are described by differential equations, partial differential equations, then we have to worry not only about the high dimensionality of the quadrature, but also how to deal with the approximation of the actual physical system. So I will I will describe then the multi-level Quasi-Monte Carlo methods and give you the analysis, or at least an idea of the analysis, and some further extension, describe some further extension, which I won't have time to give you all the details before finishing with some numerical results. So as an introduction, for those who are not familiar, and not to lose everybody on the first slide, just what am I concerned about in the context of uncertainty quantification. So the word obviously can mean many things, but as a subject of research, it typically means dealing with uncertainty in physical systems, often described by partial differential equations. And the fruit fly would be this diffusion equation in front of you here. So if we are studying many physical processes, heat conduction, subsurface flow, electrostatics, etc., then a diffusion-like problem occurs. And in many heterogeneous systems, in systems with complex media, the diffusion coefficient A of x may be quite, may not fully be certain or even unknown. And then the question arises how to deal with this uncertainty. A PDE solution is obviously an infinite dimensional object. In practice, one often is concerned mainly with quantities of interest, so with some functionals of this PDE solution. And if you have uncertainty in your coefficient A, or even in the right-hand side, or the shape of the domain, these would all be typical uncertainty quantification questions. Then this uncertainty is obviously inherited by the quantity of interest. And so one could do a worst case analysis. One could say on some ball around some nominal value, we look at the worst case, the infimum over all functional evaluations, and the supremum. That would be that sort of uncertainty interval. But in practice, some coefficients are typically more likely than others, and so very often and most commonly a probabilistic approach is used. And so we introduce a probability measure on this coefficient, which in the instance that I've described to you is a function valued coefficient, and therefore we have an infinite dimensional object. And this what I've described so far to you would then be the propagation of the uncertainty in this coefficient A to the quantity of interest. So often, even though G of U might be a scalar valued quantity, we have no access to this directly. We do need to go via our knowledge or our model of the uncertainty in the coefficient, and then via the PDE we get the uncertainty in the PDE solution U, and then only we can actually get the mean, variance, moments, or the distribution of G of U. So this would be the typical question of uncertainty propagation. But obviously, the choice of the underlying distribution on A is then in some sense subjective, and it's not always clear how you would choose it. There is some classical guidelines. So typically the next step then, which will not be the focus of today's talk, the next step is then to improve this distribution by using measured data on other quantities of interest and to do some sort of Bayesian inference, condition on the data that you measured in order to predict data that, or quantities of interest that you would like that you have no direct measurement access to. So I will talk today about the uncertainty propagation part and not about the uncertainty quantification part, but that's obviously also very important. So I promised I would say, why would I bother you with eigenproblems, and why is this an interesting object to study? And here is one example. So a typical or the common model of modeling, for example, nuclear reactors, and I actually, it was one of my first research topics because I did my master's thesis on this, is to model the distribution of neutrons in a nuclear reactor via a diffusion equation, and to initialize a time evolution of such a neutron distribution in a reactor, one solves the criticality problem. So this is the key question that one has to solve first: is what is the actual distribution in the reactor, and how do you configure the reactor? So how do you set your coefficients here, A, B, and C, which is the diffusion coefficient A, the absorption coefficient B, and the fission coefficient C in this neutron diffusion equation, which basically control whether the reactor operates in an efficient way, is self-sustaining, is not self-sustaining, or is supercritical, blows up, basically. And one has control rods that one can put into the reactor, which essentially changes all these coefficients because it's a different material than what's in the water or what is in there otherwise, where you put the control rod in. And obviously, once you run this nuclear reactor for a while, then there will be degeneration of the material. You will have certain uncertainties in the geometry of these rods. You will have not the same diffusion coefficients, absorption coefficients anymore. But as you can see here, it is a highly unstable situation. We really want this to operate this very close to 1, to this eigenvalue lambda equals 1, because otherwise the reactor will just die out, or the reaction will die out, or the thing will blow up. And so accurate calculations are very important, and therefore also accurate uncertainty quantification is important. So now, how does this differ from what I had before? Well, this is an eigenproblem. It's not only U that's unknown, but also lambda. Okay, so this is the nuclear reactor criticality problem. So how we model this in an EUQ setting is that we parameterize, well, in the most general way, you can think of any distribution on it, but very often we parameterize our distribution with an infinite sequence of parameters. And then essentially you now have a parameterized eigenproblem, PDE eigenproblem, where X is our physical dimension, physical parameter, and Y is now our stochastic parameter that describes the uncertainty. And I might not have said this before, but I will say it in a minute anyway. Obviously, an eigenproblem has not just one solution, but it has accountably many. And in the particular problem of nuclear reactor criticality, the dominant eigenvalue, the first eigenvalue, is of interest. But there's other examples, very prominent, and where I'm also involved at the moment with aeronautical engineering or structural engineering, is buckling analysis. If you study an airplane wing, for example, you're caring about the buckling of structures. Here you see an oil tanker before it breaks as it buckles, and here are cylinders buckling. You can have in electromagnetic and acoustic wave propagation, photonic band gap analysis, and as Michael said earlier, in computational chemistry, there's plenty of eigenproblems to get the ground states of certain I can't think of the word now, of certain materials. So what I'm gonna focus on today for this mathematical talk is the following. In the first instance, infinite dimensional stochastic eigenproblem. So I have the problem that I had earlier with coefficients A, B, and C. For the analysis, we have to assume that the fission coefficient, or the one of the two sides of our generalized eigenproblem, has no coefficient dependence. So we're assuming that this C of X is not dependent on the parameter, which may or may not be realistic in a realistic example, but this is what we're considering now, and I'm posing for simplicity homogeneous boundary conditions. So the grad here is always, now we have X and Y, but be aware when the grads are here, we're talking about differentiation with respect to the X variable, and we are assuming that the dependence on the parameter is we're using just a uniform distribution, but any bounded, any distribution supported on a bounded set would be fine as well. We have not considered, or we have not proved it for example, the Gaussian or normal case. Yeah. Now, what are we interested in? We're interested, for example, in some functional of the eigenvalue. So the simplest case, we just want the expected value of the eigenvalue, which is what I'm gonna basically use as the example for the whole talk. Or you could be interested in some functional of the eigenfunction, which is particularly interesting in the nuclear reactor criticality, where you might want to know about hotspots in the reactor, and you want to study for example, the average of the neutron flux in some region, in some localized region. Okay, so the coefficients, as I said, I'm assuming that the parameters are just these uniform minus a half variables, and we're assuming that A of X, Y is expanded in some generalized Cohen-Löw expansion. So you've got some eigenfunctions that describe the correlation, a spatial correlation in the random field, and the dependency is this affine dependency on the coefficients here. So it's affine in Y, and we have these eigenfunctions, or these basis functions, to expand this in an infinite series. And the same for the coefficient, the absorption coefficient B. So here is just some example that you can see what I mean by such realizations. So choosing the parameters in this way, and assuming that the coefficients, the eigenfunctions, or these expansion functions Aj, they have to be assumed to decay in size, obviously, otherwise this infinite sum would not exist. So we have to assume some summability. It's sufficient for writing the problem down to assume this with p equals 1, but for our regularity results that we need later, we're assuming that it holds for some p between 0 and 1, that we have p summability of the L infinity norm of either of those eigenfunctions here. Now, with such an assumption, you get realizations of this random field as shown in this picture. So this would be one realization, y1 here. This would be another realization. This would be another realization. So these would be 3 realizations of such a random field A, and similarly for B. So I'm just showing in 1D here, but this works obviously in any dimension, physical dimension, 2D or 3D as well. We have to assume that the diffusion coefficient and the right-hand side for our theory, the coefficient on the right-hand side are uniformly bounded away from 0, and that the lower order term we assume also is non-negative. So just to start with giving a little bit of relevant past work. So in 2012, Roman Andreev and Chris Schwab analyzed this in the context of sparse tensor approximations and proved analyticity of simple eigenpairs. Then we did a single level QMC analysis for the same problem in 2019, and this I think should say 2019 as well. Dirk Nuens with Peter Jan Robbe and Stefan van der Walle, they already looked into doing this in a multi-grid way for source problems. So this is one of the key ingredients for my talk today, and recycling samples. So both of those aspects will be key ingredients for the algorithm I'll show you today. And in particular for the deterministic algorithm underlying what I'm going to do, I refer to these papers here where in the deterministic setting, these multi-grid or 2-grid algorithms have been studied. And then there's of course a huge literature on QMC for PDE source problems already, and I'm naming just the main people, and this is not an extensive list, so I might have forgotten some. So what's our approximation strategy? We have an infinite dimensional parameter space, and we have a PDE eigenproblem. So we cannot solve this in general explicitly. So we have to both discretize the parameter dependence or the parameter expansion. We have to cut off our series basically after S terms. And we also have to discretize in space. So we have to discretize our PDE. And we will typically do this with finite elements. Now, from a point of view of today's talk, I will not focus very much on this dimension truncation. So from now on, you can basically, I will interchangeably talk about the untruncated and the truncated one, which the truncated, of course, is a special case of the untruncated one where you set the final parameters to 0. So it's like an anchored, you can think of it as an anchoring in the other dimensions, but we'll for the rest of the talk, I will assume that this is sufficiently large so that this error is negligible, but I will make sure that all our other errors or the constants in our other errors do not depend on the dimension, and which is obviously crucial to have these algorithms scale as the tolerance goes to 0. Sorry. Now, the key ingredient and the main object of today's talk is how I deal in the end with the quadrature, with working out the statistics, the expected value of some functional of the PDE solution, or in the simplest case, as I will focus on for the rest of the talk, the expected value of the dominant eigenvalue. Okay, so we will use QMC integration, which is nothing than an equal weight quadrature rule, where we simply doing sampling on deterministic points on some lattice TK, and then we simply summing up these samples. I always put like sort of inverted commas around it because they're in some sense deterministic, they're not samples. And then we divide the sum by 1/n. So this rule we denote with Qn for endpoints of lambda SH. So what's different from source problems and why is it worth a talk here? So eigenvalue problems are nonlinear. So most of the analysis that's been done so far on these QMC methods and the analysis of the convergence rates of QMC have been done for linear problems, for source problems, and eigenvalue problems are inherently nonlinear, as you have on the right-hand side lambda times u. So the second thing is that you have to concern yourself with two objects of interest, lambda and u. And therefore, the analysis that I will show typically has to do an induction over all our regularity estimates, have to do an induction over two quantities, lambda and u. You have infinitely many eigenpairs, and so you need to worry about how to handle multiple eigenvalues. And as we will see, it is actually crucial for what I'll describe today, or the theory that we've done so far, that we have a simple eigenvalue and the gap between the eigenvalue that we want to study and the rest of the spectrum. And then the whole PDE-FE analysis for eigenvalue problems has also got a different flavor, and the QMC analysis is a little bit more involved. So before going into the method, since we're using finite elements to discretize the problem, it is obviously we will pose as so far I've posed the problem as in strong form, but we will use the weak form, and we have here the weak form. We're multiplying with a test function v. Here you see we're doing integration by parts, and then we get this this variational eigenproblem, which is now got a bilinear form on the left and the bilinear form on the right, which is sort of the stiffness matrix and the mass matrix. And you're interested in the eigenvalue and the eigenfunction in this variational eigenproblem, subject, obviously, as usual with eigenproblems, to some normalization. So the norm is equal to 1. What do we know about such eigenproblems? There is countably many eigenvalues. They're real, and I'm numbering them with lambda 1 being the smallest in size. The only accumulation point is infinity. So as Lk of y, as k goes to infinity, Lk of y goes to infinity. And with the assumptions I've made about my coefficients being strictly bounded away from 0, the lambda 1 is simple. And for simple eigenpairs, lambda u are analytic in y. So this is the result I mentioned already by Andreev and Schwab. And the lambda 1 is bounded independently of y as well. So for now on, we're gonna from now on, I'm gonna consider the minimum eigenvalue, and I'm, as I said earlier, fixing the dimension truncation sufficiently high, and I will ignore, to simplify the talk, the truncation error. So why is simplicity important? Here, what I mean by simplicity is if you look at lambda 1 and lambda 2 as functions of y, you want basically to have a non-zero gap between those two paths all along. You do not want to have this situation where you might have crossing eigenvalues or touching eigenvalues, because essentially almost all the results we're quoting and using are relying on this gap being non-zero. So obviously, there is room for also considering log normal type problems for the specialists, because obviously even log normal problems have very low probability that the gap goes to 0. And you can do analysis as we did with source problems in some LQ sense. But for the moment, we are assuming it in a uniform sense. So that really the gap is non-zero. And in fact, this what we actually managed to prove. So here, as I said, many of the results break down. So the finite element and dimension truncation errors depend on the gap. The convergence of eigensolvers, so iterative eigensolvers is what we're going to use to find these eigenvalues, because these matrices are huge and you do not want to factorize them. So those degrade when the gap gets smaller, these eigensolvers, and the stochastic derivatives, as I'll show you later, depend on 1 over this gap. So in the single level QMC paper with Ivan Graham, Francis Koo, and Ian Sloan, Alec and I managed to show that this gap, in fact, is bounded away uniformly from 0, under the assumption that we have this p summability for some p less than 1. And this was kind of missing in the Andreev Schwab paper, because they just assumed this, and we managed to prove this. And it was a little bit of extra work and a very elegant solution, I find, because obviously in the infinite dimensions, the minus a half to the n is not compact. So one could use different topologies to analyze this than the infinity topology, but because we assume this slightly stronger summability, we just simply rescaled the problem, put a little bit of the a to the j onto the y, and that allowed us to prove this uniform boundedness of the gap. Okay, so this was the first ingredient. So we need this bound on the gap. The second ingredient, as I said, is some form of discretizing the PDE, and we're using, in the simplest case, and for this paper, simply piecewise linear finite elements, but high order finite elements would also work equally well. Now, in the finite element method, essentially what you do is you replace your space, now your spatial function space V, by a finite dimensional subspace, and you parametrize this with the mesh size h. So as h goes to 0, the subspace gets larger and approximates better and better the infinite dimensional subspace, infinite dimensional function space V. And we can then use deterministic results about eigenvalue problems to see that the eigenvalues for the piecewise linear case converge quadratically. So the first eigenvalue, lambda1 or lambda1h with the finite element method converges quadratically to the first eigenvalue lambda1 of y, pointwise in y, with a constant that's again independent of y. But crucially, of course, depends on the gap. Now, once we've chosen a basis for this subspace VH, then you can think of it simply as an eigenproblem, as a matrix eigenproblem. So then you have a large, sparse, stiff finite element stiffness matrix here, and a mass matrix on the right-hand side, and you're interested in the coefficient vector in our basis. But obviously, again, except BH, all of our objects are now parameter dependent, depend on y. And here you see now the nonlinearity, of course. Okay, now, as I promised, we will use Quasi-Monte Carlo integration, and in particular, we will use randomly shifted lattice rules. And those are simply constructed by taking a suitable generating vector and then basically that here's a 2D picture that basically gives you the slope of these lattice, how it's lying diagonally in our unit cube, in the minus a half cube, and then you essentially iterate, or you take k from 0 to n minus 1, and that gives you these points along these lattice lines here, these red points. In order to make this an unbiased estimator, and in order to also help with the analysis and other aspects, we are shifting it randomly. This is also a common technique. So we're just shifting the these point set by some random vector, so the same vector for all points. So the whole lattice essentially is shifted in space. And in order to get this lattice points to lie within the unit cube, we use this curly bracket here, which essentially always truncates it back into the unit interval from 0 to 1, and we take -1/2 to get it back into the interval -1/2. So for those who have never seen QMC methods, this might be, or lattice rules, this might be a bit too speedy, but in essence, it's a deterministically constructed rule for which we can make rigorous error bounds in terms of how well they approximate the integral if we're using them within this these equal weight lattice, equal weight quadrature rules here. And there is efficient constructions. CBC stands for component by component. One starts with the first component of the vector Z, and then in a greedy fashion computes the further components in this vector Z. Okay. Now by now standard. So in the past we would always have said the new weighted analysis, but nowadays one would have to say the standard QMC error analysis for such a rank 1 lattice rule is done in weighted mixed smoothness spaces. So the importance being that we really require mixed derivatives here. So as we look here in this norm, in this WS gamma space, we are interested to control mixed derivatives. For the randomly shifted rank 1 lattice rules I'm describing, we only require mixed first derivatives. So this notation here stands for derivative with respect to all variables in the subset nu of 1 to s that are in this subset nu active. So you pick all possible active subsets nu, and then you differentiate with respect to those variables, take the mixed first derivative with respect to those variables, and then you weight with this 1 over gamma or gamma nu. So this is these weighted mixed smoothness spaces that are used for now analyzing QMC rules. Now, with the component by component analysis and the classical theory, the error bound is then essentially nicely splitting into a worst case error given such a lattice, which can be shown to go like n to the minus some power that depends on gamma, and the norm of the integrand in this weighted norm I've just sort of sketched. And the crucial thing is then how to choose these weights gamma and the value of delta here in such a way that the constant C delta gamma is independent of the dimension S. So this is the crucial task. Because in the what people are familiar with the old QMC analysis, there would always be an n log n to the d, or log n to the s, sorry. S is our dimension here. And then we still have exponential dependence on the dimension, which in this weighted analysis is not there. And it relies on this assumption I made at the very beginning about our coefficients, namely that the weight in this expansion decays. So the norms, the infinity norms of these eigenfunctions decay. That's crucial in order to be able to get this dimension independent bound. Okay, so in order to analyze this, we need to show that our eigenvalue is in this mixed smoothness space, in this weighted mixed smoothness space. So in the 2019 paper, we showed, I've already said that the eigenvalues go like order h squared. The cost of an iterative eigensolver, like inverse iteration, would be number of iterations of this inverse iteration method times a PDE solve. And a PDE solve is typically h to the minus gamma for some gamma bigger than the spatial dimension d. And if this can be done for this elliptic problem I'm using as my model problem with multigrid, with algebraic multigrid, then this gamma you can think of as being slightly bigger than d. So gamma is slightly bigger than d. The convergence rate is 2. Then in this single level paper, we were able to show that under the assumptions I've given you, with the p sufficiently small in our summability of the coefficient, we can actually obtain order n to the minus eta convergence of our QMC error bound, convergence error bound, and with eta being somewhere between the Monte Carlo rate 0.5 and 1, depending on the value of p. Now, given that, we can then do a complexity analysis and epsilon cost analysis for both of those errors to be less than epsilon. One needs then to do epsilon to the minus 1 over eta plus gamma over 2 operations, which in the Monte Carlo case would be epsilon to the minus 2 minus gamma over 2. Remember, gamma is about d, so in 2D this would be 1 here. And the QMC in the best case for sufficiently fast decaying dependence on the coefficients, we gain a whole power. So we have epsilon to the minus 1 minus gamma over 2. And I'm seeing that I'm running a little bit out of time. So the error analysis relies on a regularity result. So one needs to prove that the mixed smoothness of this eigenvalue is grows not too fast. So essentially we have this dependence on the coefficient eigenfunctions. So this is where the summability will come in on these L infinity norms of the basis functions of our coefficient. And I've explicitly stated here how it depends on the gap. And for those who are familiar with the theory, in comparison to the theory in the source term problem, we have this extra epsilon term because we have to do an inductive argument over both the eigenvalue and the eigenfunctions and swap and go between the two. So we lose a little bit here, but it doesn't really matter. It only matters in the case when p is on the limit equals 1, and in all other cases for p it doesn't matter that we have this slightly faster growth with this term here. As I said, I need crucially the gap to be uniformly bounded, and then one minimizes the error bound by choosing the weights appropriately. This is the CBC construction, and delta is then chosen so that the S the constant doesn't depend on S. So here is an example. I've set B to be 0, and I'm only looking at the diffusion side on the left-hand side. I've got one of those sort of pseudo KL expansions with a decay that's algebraic. So if I choose Q equals 2, this will be quadratic decay here in the eigenvalues. And I'm using S equals 100, mesh size 1/256. And you see very clear that the QMC convergence rate is essentially order 1 on n. So we have gained the whole order, and we have also got quite a significantly better constant. So the curve is actually significantly lower down as well. So what about multi-level now? If I want to do this eigenproblem now in a multi-level fashion, and I've seen already several talks in this conference, so people are familiar with multi-level quite well now, we are, instead of just doing one QMC estimate, we're gonna take a collapsing sum of approximations of our eigenvalue, and then we're summing up the quadrature rules for the differences. So delta L, lambda L would be the difference of lambda on level L and on level L minus 1. And then the multi-level estimator would be the sum of those. So now, depending on how you choose your estimator or your quadrature rule here, you get multi-level Monte Carlo, multi-level Quasi-Monte Carlo, multi-level stochastic collocation, and you get essentially a sum of Monte Carlo or Quasi-Monte Carlo estimators. I'm going to skip this people have seen this many times now. So the key idea of multi-level is that on the coarsest level, each sample costs me only order 1, but I need to do order epsilon to the -2 samples. So the cost on the coarsest level is order epsilon to the -2 coming from the Monte Carlo. This is the Monte Carlo case from the Monte Carlo quadrature. Whereas on the finest level, where I have a good finite element error approximation, the difference, the thing I'm integrating, the integrand delta lambda L itself is of order epsilon. So the integrand is of order epsilon, so I can get away with only doing order 1 samples. And then the cost for the finest level would be order epsilon to the -gamma/2. So here we have on the coarsest level order epsilon to -2, and on the finest level order epsilon to the -gamma/2. And this can be formalized in these classical multi-level complexity theorem, which here I'm now stating because in the QMC setting, we have we don't have the n to the -1/2 in general, or n to the -1 in this variance estimate here. And in Aretha Teckentrupp's thesis already, she generalized the complexity theorem to this more general setting, which applies in particular for the QMC case. So essentially, the jump where we jump between one regime where the coarsest level dominates and where the finest level dominates is scaled by this gamma, by this eta, sorry, which is the coefficient in this convergence rate for the quadrature rule. And you can have any order here, for example, for multi-level stochastic collocation, this could be significantly higher than for Monte Carlo. Now, using this with Alec, we could now do a specific result for the eigenvalue problem I've given you. And for that, I'm only giving you a partial result. So we can do it for any p between 0 and 1, but I'm only going to give you the result for p less than 2/3, because for p less than 2/3, we get the full power of QMC. We actually get order epsilon to the -1 plus delta. So any delta, so essentially almost order epsilon to the -1 in the best case where the dominating cost is on the coarsest level. Okay. And what we need to assume is, in addition, and maybe that's not so visible here, we need to assume that not only do we need some ability on the AJ and the BJ in the L infinity norm, we also need it on AJ in the W1 infinity norm. We need some ability on the gradients of our coefficient. But comparing to what the other methods would do, Monte Carlo would have the rate would be epsilon to the -2 gamma/2. QMC, as I showed you before, is 1 order better. Multilevel Monte Carlo, I already showed you on the previous slide, is the maximum of 2 in gamma/2. And here we have the maximum of -1 and gamma/2. So we gain potentially an extra power. So the first assumption in our complexity theorem is, again, just the finite element convergence result, which I've given you. What's the key result for the multi-level QMC analysis, which is also what's the length of the paper, why the paper is actually in two parts, is we need to prove mixed spatial stochastic regularity. So here we have got derivatives with respect to x and derivatives with respect to y. And we need to prove that the solution has actually this mixed regularity. But we can prove this, and we get a very similar bound, simply that here now the gradient, or the L infinity norm of the gradient of AJ also pops in. But it again depends on the gap, and it again depends on this new factorial to the 1 plus epsilon. And this can be done by taking the strong form of the eigenproblem, differentiating, and then using the Leibniz rule and induction and some combinatorics. Now, finally, to prove M2, we then also write down this variational equation, which is essentially obtained by subtracting and manipulating the variational problem and the approximation of the variational equation in the finite element space, and then differentiating with respect to the parameters. Now this, manipulating this around, we get a very similar bound also for lambda minus lambda h, or the derivative of lambda minus lambda h, which again has the same constants here, depends on the gap, and has now this, what we require, this variance reduction aspect. It has an h squared popping out. So this is the crucial thing we needed to get in order to get M2, and therefore to get our result. I'm gonna skip this, so I'll leave the slide up a bit, so if somebody watches the video, they can have a look at it. This is now an extra extension we do where we can use a so-called two-grid finite element method for eigenvalue problems, which is particularly well suited in the context of multi-level QMC, because you only ever solve coarse eigenvalue problems. So you only ever solve eigenvalue problems on a coarse finite element space, and on the fine finite element space, you only need to do one correction equation, so one source problem. So that means there's no iteration necessary on the fine scale space anymore, and the size at which you can do the coarse problem is significantly coarser. So you really can you can basically forget about the cost of the eigenproblem. You just have one source problem to solve. And we do this from one coarsest problem. We essentially build all the two-grid estimates, all these differences in our multi-level estimator we built from one coarse one. And this is not restrictive because, as I told you, it's power 4. So if I choose the coarsest level to be 1/8, I can go all the way up to 1/4000. So I can go to very fine grids. Okay. We can also use nearby QMC points, as was done in the paper by Peter, Jan, Robbe. But we also have some theory for that. And we can include the truncation error analysis, and we can do functionals of the eigenfunction as well. And maybe for those who want to continue with this work, the regularity bounds in the paper are actually done for general higher order mixed derivatives. So this might be of independent interest if one wants to do, for example, stochastic, Galerkin stochastic collocation, or high order QMC. I'll finish with a bit of numerics on the multi-level. This is the same problem I showed you before, very similar problem, again with Q equals 2 quadratic decay. We're using here an off-the-shelf lattice rule from Francis' webpage, and we're fixing the truncation dimension. And you see the typical picture. If you've seen these pictures before, you've got your Monte Carlo convergence, which is epsilon to the -3 in this example. You've got your single level QMC, which is not completely in the asymptotic regime yet, but should be epsilon to the -2. Similarly to the multi-level Monte Carlo, the red line here. And then you've got our method, the multi-level QMC, which is essentially epsilon to the -1. And the black line is when you add this two-grid acceleration, which might not look very impressive on this example, but that's just because the eigensolver converges so fast in this simple example. So here is a harder example with some jumping coefficients. And then you see that essentially the rate, we will not get a better rate with this two-grid method. It just improves the constant, but the constant is improved by a factor 2 to 4. So in practice, this is a significant gain. Okay, so in summary, I've shown you how to design multi-level QMC methods together with two-grid finite element methods for UQ in eigenvalue problems, and shown you that the speedups through QMC and multi-level are complementary. And I have not shown you, but there's also similar results for linear functionals. And as I said already, there is avenues that could be investigated further, like higher order QMC rules, log normal coefficients. And one thing we are working on at the moment is to extend it to other eigenproblems, such as non-symmetric eigenproblems. Okay, and maybe the only thing to point out, these are the two papers that I've just presented at the bottom. Thanks for listening.